Calc 2, Test 1 will be tomorrow, and that's covering the Think Well chapters 14 and 15, what we've been working on so far. The worksheets, well, it's been, 8.7 and 5.6, 5.7, 5.8, and then a couple that I made myself. So, but what we looked at in chapter 14, finding limits using L'Hopital's rule. I guess make it official here. So anytime, now remember this is calculating a limit. Well, when we get either 0 over 0 or positive or negative infinity over infinity. So if it's not in that form, then you have to manipulate it to get it in that form. And believe me, there will be at least one or two like that. So, but some will be fairly straightforward. By now you'll be going, oh, that's easy, or at least you should be. But there will be maybe one or two that aren't quite so easy. Let's see. With this as well, there might be something like that. What would we need to do with something like that? Right. That's where we got to manipulate it with the natural log. We can either use his notation, change this precisely into e to the natural log of this, or what I did was change the whole thing, let y equal this, and then natural log of y equal natural log of this. But eventually, whichever notation you're using, you'll need to pull the 1 over x, the exponent part, out in front. And my notation, you can end up with that, which would simply be natural log of x over x, and go from there. Or with his notation, you'd have e to all of that and work from there. One problem, I guess you would say, with my notation, once you find the limit, then you'd have to go back and say e to that power. But don't forget that last little step. Once you get the limit in my notation, you've got one more step to do. Whereas keep it in his notation and it's already there. Procedurally, we do the same thing. It's just more a notation difference. Yep.
It's like doing like the dy over dx, and then it'll be equal to that answer times your y.
So,
you know what I'm saying, right?
Kind of.
Like you're gonna derive that and then multiply times.
Yeah.
Times
Find
y, right?
find your limit of this as x approaches 0, and you can use L'Hopital's rule on it. And then, actually, I don't know that that's the correct form. Procedurally, this is what you'd do, but I'm not sure we'd have x to the 1 over x. Might be more like x to the x.
Rather than natural log of x be infinity.
Yeah. As x approaches 0, natural log of x would be negative infinity. So, yeah, my starting point here would not be right. If we go x to the x, I think we'd be okay. But same procedure anyway. And then that way, over here, we'd have x natural log of x, and then we'd need to change that to natural log of x over 1 over x.
Okay.
And there, yeah, we'd have a negative infinity over a positive infinity. So we could use L'Hopital's rule from there. So, yeah, good question. Sometimes when I make things up off the top of my head, it doesn't quite fit like I want it to. But anyway, that will definitely be one of your biggest, longest L'Hopital's rule to work through. And then again, if you don't have the E like he does, make sure you convert it back into E2, whatever that limit value is. Okay? Okay, so L'Hopital's rule, we did look a lot at L'Hopital's rule. We spent several days on that, so I'm not saying that's going to be the majority of the problems, but there will be a pretty decent number of problems there. I guess I should say there are going to be 20 problems. So in this test will be very similar to the size you saw in Calc 1. I will count each one worth 5 points and kind of your typical one there. But 20 problems, and as I've said earlier last week, you do get 1 sheet of paper for notes, front and back. I guess I should say 8.5 inches by 11 inches. Your standard size paper can't have 8.5 foot by 11 foot for your note card, but standard sheet of paper. Get my units on there. I dog you guys if you forget your units, but of course in this chapter we haven't had any applications, so you won't need units on it, but we'll be looking at a lot of applications through the semester. So okay, so L'Hopital's rule, probably 6 to 8 problems using L'Hopital's rule. Like I said, we spent quite a bit of time on it, so we'll have plenty of problems there to look at. So Chapter 14 with Think-Well material was L'Hopital's rule. Chapter 15, we get into some kind of special types of functions. We looked at the log functions. Now, these would be the log functions of different bases, different from your natural log, but maybe a log base 2 or log base 10, something like that. And calculating the derivatives. Then we kind of stepped it up a notch and looked at a function, I'll say an ugly function, not necessarily a log function, but an ugly function, and using what we call logarithmic differentiation to find the derivative. So, and the benefit both for the basic log function and for these ugly functions that we turn into a logarithm, using the log properties to rewrite the original function to make it a lot nicer to work with before we take the derivative. Because you're going to, especially this particular problem, you're going to see one ugly function. It's possible to do it with just your basic derivative properties, but just run through one real quick. Let's see, let's go 1 minus x cubed. Let's say this is our function, And yeah, really ugly. What we can do is take the natural log of both sides. Now I'm going to change f of x into y, make notation a little bit easier. So we'll go natural log of y equals the natural log of all of this. Now one thing that will help with this notation is changing that to what? Instead of a cube root, raised to the 4/3 exponent. Change your root into a fractional exponent. And then this side we can manipulate a lot with your log properties. And like I usually do, I don't leave enough room. We'll kind of do a few of these in the little space here that we have. We can look kind of at this in three parts. We've got x squared times this part and then divided by this part. When we multiply inside a logarithm, we can do what? Okay, break it up and add them. So natural log of x squared plus natural log of our next part, and then what about the bottom part?
Subtract.
Okay, minus that to the third. And then finally we can apply the exponent property. Now remember, all of this is just algebra. We haven't done any derivative yet. And with our exponent property, I'll transfer that to the top of the next page. We have our natural log of y on the left side, and then natural log of x squared would be your 2 natural log of x, plus that natural log to the 4/3 power. Let me pull that 4/3 out in front. And that was what? X squared minus 3x plus 2. And then the minus 3 natural log of 1 minus x. So that is about all we can do. There might be something more we could do on the inside here, but at this point that's plenty good. We've got our exponents out of the way. That's what makes the derivative so much more involved when you have to do a chain rule. But with this, we're now ready to do the derivative. But what you need to remember is it's not just dy by dx equals, or y primed equals, but natural log of y will have 1 over y times the y primed. And then at the very end, we'll have to multiply both sides by y, by the original function, and then times whatever is left on the right side here. So derivative of natural log of x, well, that's about as easy as you can get. 4/3. Now this one will have 1 over the inside, and then times the derivative of the inside, and then minus 3, 1 over the inside, times the derivative of the inside. In this case would be just the -1. Be careful with those signs. 1 minus x, you need your -1 out there. And so, okay, we'll kind of rewrite some of this as we go as well, but we'll have the y, whatever our original function was, I'll try to remember it here, x squared times the cube root of x squared minus 3x plus 2 to the 4th power all over 1 minus x quantity cubed. Okay, that would be the y that we're multiplying on the other side, and then times what's left here. Of course, we can rewrite it a little bit. We'll have 2 over x plus 4 times 2x minus 3 all over 3 times our x squared minus 3x plus 2. And then this last part we'd have, plus 3 over 1 minus x. And that would be the correct answer of use logarithmic differentiation to find the derivative of this function. Now, most of the time on problems, I just say find it. Do it whatever way you want to. But there will be at least one problem that I say use logarithmic differentiation to find the derivative. So you got to go through this procedure in order to get credit for that. Okay? And that too also shows you the benefit of our log properties when finding your derivatives of logs if you're in a different log, base 2 or base 10, something like that. Okay? But definitely have your derivative of log x base a formula written down, and then make sure you know how to manipulate your logarithms to make things a lot easier. Some of these are much easier after doing the log properties than trying to take the derivative before. Okay, so that was kind of our first set of functions working with the derivatives. Then our next set, we kind of introduced your inverse trig functions and then looked at the formulas for the derivatives of the inverse trig functions. Now, we looked a lot at the inverse trig function values in the 5.6 worksheet. I'm not going to have anything about trig values. Nothing like that on the test. You will see the inverse trig functions find the derivative of inverse trig functions, but to kind of see where those derivative formulas come from, you have to have the idea of the inverse trig, the values like we were doing on 5.6, the first part of 5.6 anyway. But find things that will be on the test, find derivatives of the inverse trig functions, which was the first part of the 5.6, 5.7 worksheet. And while we're at it, 5.8 worksheet was the hyperbolic functions. Again, I'm not going to have anything in particular about the algebra of hyperbolic functions. Hyperbolic.
Are you going to have the antiderivatives too? The inverse trig function?
Yeah. So derivatives will be your inverse trig function derivatives and the hyperbolic function derivatives. And then there'll be a handful of the antiderivatives.
So you're saying that there's not going to be hyperbolic functions?
The 5.7 part on your worksheet was the antiderivatives of your inverse trig functions, or actually taking the antiderivative of something and you end up with your inverse trig function. So reversing the derivative part. Okay, so the only thing that we'll have to worry about with the hyperbolic functions are the derivatives. Find the derivative of the hyperbolic sine of x. Of course, it won't be that easy, but something like that. But I'm not going to have you do like the algebra part of evaluate hyperbolic sine of 1 or working through those identities. Those are just kind of a building up to those types of functions. So, but you will need to know the derivatives of your hyperbolic functions. Okay? Questions there? So that's really all of the test. As I said, L'Hopital's rule will be first several problems. Then we'll have find the derivatives, which could be inverse trig functions, could be log functions, could be the hyperbolic functions. So most, the largest portion of the test will be find derivatives. But it's going to be those 3 different types: log, inverse trig, and hyperbolic. Make sure you have all those formulas down on your sheet. This is the main reason I give you the sheet of paper, because I don't remember all of those off the top of my head. So I'm not going to make you guys memorize them. And then finally, the last few antiderivatives, we do a few of those, but not too many of them. So probably 3 to 5 of those will be plenty. Okay? And along with the derivatives, that logarithmic differentiation might be 1 or 2 of those. So there's what's going to be on the test. Do you have any particular questions, any problems you want to see?